Imagine waking up in the middle of the ocean as a massive storm throws a ship from side to side. Outside, waves rise like walls, while deep below the deck, sailors are still resting in their cabins. How can they sleep when the entire ship is moving beneath them? What systems keep the vessel stable, and what protects the people inside? In this documentary, we'll go inside the ship and uncover the engineering behind survival at sea. Subscribe for more incredible engineering stories, and let's go inside. A ship does not tilt randomly. During a powerful storm, waves striking from the side create a force that pushes the vessel away from its upright position. This movement is called roll. The larger the wave and the stronger its impact, the greater the rolling motion can become. But the ship's hull and underwater shape are designed to resist this movement and generate forces that help bring the vessel back toward an upright position. A ship can move in several directions at once, but three motions are especially important in rough seas. Roll is the side-to-side rotation around the ship's length. Pitch is the up and down movement of the bow and stern. And yaw is the turning motion around the ship's vertical axis. During a storm, these movements can combine, making the vessel feel unpredictable. Understanding them is essential because engineers design the hull, propulsion, and control systems to manage these forces. When a ship rolls, two important forces determine what happens next: gravity and buoyancy. The ship's weight acts downward through its center of gravity, while the surrounding water pushes upward through the center of buoyancy. When the vessel tilts, the underwater shape changes, shifting the buoyant force. This creates a restoring moment that can push the ship back toward upright. It is one of the fundamental principles that allows a properly designed vessel to survive repeated movement at sea. The hull is more than a shell around the ship. Its underwater shape determines how much water is displaced and how buoyancy changes when the vessel rolls. As the ship tilts, one side of the hull sinks deeper while the opposite side rises. This uneven displacement shifts the buoyant force and can create a restoring moment. Engineers carefully design the hull's width, depth, and underwater geometry so the vessel can resist rolling and return toward a stable position. Deep inside many large ships are ballast tanks, spaces designed to hold seawater when needed. By controlling the amount and distribution of this water, the ship's weight and balance can be adjusted. Ballast is especially important when cargo, fuel, or other loads change the vessel's condition. During rough weather, proper ballast management helps engineers maintain the ship's design stability and keep the hull safely positioned in the water. Ballast only works when its distribution is carefully controlled. If water is concentrated unevenly, it can change the ship's trim or stability. Pumps and valves allow seawater to be moved between designated tanks, adjusting the vessel's condition when necessary. But ballast is not a simple switch that makes a ship safe in every storm. Its use depends on the ship's design, loading condition, and operating situation. The goal is to keep the vessel within its safe stability limits. When a powerful wave hits a ship, the impact is transferred into the hull and its internal structure. The outer shell takes the first load, while frames, beams, and bulkheads distribute forces throughout the vessel. The ship is designed to flex slightly rather than behave like a completely rigid block. This controlled flexibility helps prevent concentrated stress from damaging one small area. During severe weather, the hull is continuously absorbing and distributing forces from thousands of tons of moving seawater. Inside the hull, strong watertight bulkheads divide the ship into separate compartments. Their purpose is critical. If water enters one section, these barriers can limit how quickly it spreads to other areas. During rough seas, they also add structural strength by connecting different parts of the hull. This compartmentalized design means the ship is not simply one enormous empty space. Instead, it is a network of reinforced sections, each helping protect the vessel's structure and the people working inside. Deep inside a ship, a sailor's cabin is designed for a moving environment. The bunk is usually positioned securely against the structure, while doors, lockers, and other equipment are designed to stay closed or secured. During heavy rolling, loose objects can become dangerous, so anything that can move must be controlled. The cabin may still feel the ship's motion, but its design helps turn a constantly moving environment into a safer place for rest. A bunk at sea is not just an ordinary bed. It is fixed to the ship's structure and positioned to reduce the risk of a sailor being thrown around during normal ship movement. In rough conditions, sailors also follow operating procedures that determine when and where they rest. The important point is that the bunk moves with the ship rather than sliding independently across the cabin. It becomes part of the vessel's structure, creating a controlled place for rest even when the sea outside is unstable. On a working ship, rest is organized around a watch system. While some crew members are resting, others remain on duty to monitor navigation, machinery, communications, or safety operations. During rough weather, this continuous watch becomes even more important. The ship cannot simply stop because the sea becomes dangerous. Different crew members rotate through their duties, allowing essential operations to continue while others receive their required rest. When a sailor goes off duty, the ship does not stop operating. Critical systems continue running, while other crew members remain responsible for navigation, machinery, and safety. Resting crew members stay in designated accommodation areas, while duty officers maintain the watch. This separation allows the ship to keep functioning around the clock without requiring every sailor to remain awake continuously. In a serious storm, maintaining both operational watch and proper crew rest is essential for safe decision-making. When a ship rolls heavily, even a normal corridor can become difficult to cross. The deck moves with the vessel, while gravity continues pulling everything downward. That is why ships use handrails, secure doorways, and carefully designed passageways to help crew move between work areas. During severe weather, crew members also avoid unnecessary movement whenever possible. Every step inside a moving ship requires awareness of the vessel's motion and the surrounding environment. Inside a moving ship, small design details can make a major difference. Continuous handrails give crew members something stable to hold while the vessel rolls. Watertight doors, meanwhile, separate important compartments and help control the spread of water if a section is flooded. These systems are not designed to stop the ship from moving. Instead, they allow people and the vessel itself to remain organized and protected while the ocean outside continues to push the ship in every direction. High above the ship, the bridge is where the crew continuously monitors the vessel and its surroundings. Radar, navigation displays, weather information, and visual observation help officers understand what is happening outside. During a storm, visibility can drop dramatically, so electronic systems become especially important. The bridge team uses this information to maintain a safe course and respond to changing sea conditions. Every decision must account for the ship's speed, direction, waves, wind, and surrounding traffic. When rain and darkness make the ocean difficult to see, radar becomes one of the bridge's most valuable tools. It sends radio signals outward and detects their reflections from objects around the ship. This helps officers understand the position and movement of nearby vessels, coastlines, and other targets. Radar does not predict every wave or remove the danger of a storm, but combined with navigation systems and weather information, it gives the bridge team a much clearer picture of the environment around them. Deep inside the ship, the engine room contains the machinery that ultimately drives the vessel forward. The main engine produces mechanical power, which is transferred through a large rotating shaft toward the stern. Depending on the ship's design, reduction gears or other transmission components may control the speed and torque reaching the propeller. At the stern, the propeller converts that rotation into thrust, pushing water backward and the ship forward. This entire power path works continuously while the vessel is underway. At the stern, the propeller is where the engine's mechanical power becomes forward thrust. As its blades rotate, they accelerate water backward and create an opposing force that pushes the ship forward. The propeller must work efficiently even when the sea is rough and the hull is moving through waves. Its diameter, blade shape, rotation speed, and position behind the hull are carefully engineered. This simple-looking component is actually one of the most important pieces of machinery keeping a massive ship moving. A massive marine engine needs a continuous and carefully controlled fuel supply. Fuel is stored in dedicated tanks and passes through pumps, filters, and conditioning equipment before reaching the engine. These systems remove unwanted particles and help deliver fuel at the pressure and temperature required for efficient combustion. Deep inside the ship, pipes, valves, sensors, and pumps work together as one network. Without this controlled fuel system, the main engine could not maintain the steady power needed to keep the vessel moving. Inside the main engine, precisely controlled fuel is injected into the combustion chamber, where it burns with compressed air and releases energy. That energy pushes the engine's pistons, turning the crankshaft. The crankshaft then delivers mechanical power into the propulsion system we saw earlier. Every stage must happen at the correct timing and pressure. What looks like a simple fuel line from outside is actually the beginning of a complex chain that transforms stored chemical energy into the mechanical power driving the ship. A huge marine engine produces enormous heat while converting fuel into mechanical power. Without a cooling system, critical components could quickly exceed their safe operating temperatures. Pumps continuously circulate cooling fluid through passages around the cylinders and other hot components. Heat is then transferred away through dedicated cooling equipment before the fluid returns to the engine. At the same time, lubricating oil reduces friction between moving parts and carries away additional heat. Together, cooling and lubrication allow the engine to operate continuously under heavy load. Inside a massive marine engine, moving metal parts face enormous friction and pressure. Lubricating oil creates a thin protective layer between these surfaces, reducing direct contact and wear. Powerful pumps continuously circulate the oil through bearings, the crankshaft, and other critical components. The oil then carries away heat and contaminants before passing through filters and cooling equipment. Finally, it returns to the engine, creating a continuous cycle that helps the machinery operate reliably for long periods under heavy load. After combustion, the engine produces hot exhaust gases that must be safely directed away from the cylinders. These gases first pass through the exhaust system and can drive a turbocharger, helping compress fresh intake air for the engine. They then continue through large exhaust pipes toward the ship's funnel. Along the way, temperature, pressure, and emissions are controlled by specialized equipment. Deep inside the ship, this hidden network allows the engine to breathe continuously while safely removing the gases produced during combustion. Inside the turbocharger, hot exhaust gases spin a turbine at high speed. That turbine is connected to a compressor on the same shaft. As it rotates, the compressor forces more fresh air into the engine's cylinders. More air allows the engine to burn fuel efficiently and produce greater power from each combustion cycle. In this way, energy that would otherwise leave as exhaust is partly recovered and used to improve the engine's breathing and overall efficiency. A modern ship is more than an engine and a propeller. It also needs a constant supply of electrical power for navigation, communication, lighting, pumps, control systems, and crew facilities. Large auxiliary generators convert mechanical energy into electricity and distribute it through the ship's electrical network. From the main switchboard, power is sent to different sections and critical systems. If one generator becomes unavailable, other generators can help maintain essential operations, giving the vessel an important layer of redundancy while at sea. Electricity generated on board must be distributed safely to many different systems. The main switchboard acts as the central control point, receiving power from the generators and directing it through separate circuits. Circuit breakers can isolate a faulty section, helping protect the rest of the electrical network. From there, power reaches navigation equipment, pumps, lighting, communication systems, and other essential loads. This organized distribution allows the ship to keep critical systems operating even when individual electrical sections require maintenance or become unavailable. A large ship can spend weeks at sea, so carrying enough fresh water is essential. Many modern vessels use desalination systems to produce fresh water from seawater. A common method uses heat and evaporation, while other systems can use membrane technology. The produced water is then treated and stored in dedicated tanks before being distributed around the ship. This hidden system supports drinking water, food preparation, cleaning, and other daily operations without relying entirely on supplies from land. Once fresh water has been produced, the ship still needs to distribute it efficiently. Pumps move treated water into storage tanks and then through a separate freshwater network. From there, pressure-controlled lines can supply cabins, kitchens, bathrooms, and other working areas. Different tanks and pumps provide flexibility as water demand changes during the voyage. Deep inside the vessel, this network operates almost invisibly, allowing hundreds of daily activities to continue without the crew needing to think about where every drop of fresh water comes from. Even a massive ship can roll significantly when large waves strike from the side. To improve comfort and stability, many vessels use stabilizing systems that reduce this motion. Fin stabilizers extend from the hull below the waterline and generate controlled hydrodynamic forces as the ship moves through the sea. Sensors and control systems continuously adjust their angle according to the ship's motion. Working beneath the water, these hidden components help reduce excessive rolling and keep the vessel more stable in rough conditions. When a wave pushes the ship to one side, motion sensors detect the change almost immediately. The stabilization system responds by adjusting the underwater fins to create a counteracting force. As the vessel moves through the next wave, the fins continuously change their angle to reduce excessive rolling. This happens automatically and repeatedly, without the crew manually controlling every movement. The result is a smoother and more controlled ride, while the ship's hull continues to move naturally with the surrounding sea. From the machinery deep inside the hull to the systems keeping the vessel stable, every component has one purpose: keeping this massive ship moving safely and efficiently. What appears from the outside to be a single steel structure is actually a complex world of engines, pumps, generators, controls, and hidden engineering. And that is what makes modern ships so extraordinary. If you enjoyed exploring this ship from the inside, subscribe for more cinematic engineering documentaries.